not real thrilled with the PowerPoint because it's got so much things that are overwritten. I'm not sure what's provided, not sure if that's really the best focus. So what I've done is actually opened your book, and I've opened it to page 634, and I wanted to work a problem in which the data alone is provided and then talk through a setup without any structure provided on those PowerPoint slides. So I think sometimes that's distracting us if the answer's already there and you don't see where they're coming from. So I'm going to read through 14.9. It's on page 634. It has a title here. We're going to find equilibrium concentrations from initial concentrations and the value of the equilibrium constant. So we're given initial. Whenever I'm told that we're given initial values, I think ice chart. Let's record, and I'm just going to do this on a scrap paper, so I'm going to move my book out of the way. I like to give myself plenty of room, so I'm going to turn this sideways. And I'm going to record the problem. You can follow it right on page 634 where it says nitrogen gas plus oxygen gas, N2 plus O2, is in equilibrium with 2NO. They're all in the gaseous phase. We also know Kc, it's provided for us as 0.10, and it's at 2,000 degrees Celsius. So they're running this experiment quite hot. Alrighty. So there's the chemistry, nitrogen and oxygen in equilibrium with NO. It also is telling us initial concentrations. So as I create an ice chart, I stands for initial. The molarity, that's what brackets are. The molarity is 0.2 molar for the nitrogen, 0.2 molar for the oxygen, and that's it. 0 for the product. That's the information, and it's asking us, and again, just kind of sharing this again, 0.2 molar nitrogen, 0.2 molar oxygen, no product in there. Find the equilibrium concentrations for the whole works, reactants and products, at that temperature. Alrighty, so move the book out, get my calculator ready. So we know a Kc, we know the initial amounts. When the reaction proceeds, there is only one direction possible with this reaction. I have no product, so the reaction only has one choice, and that's to move in the forward direction. That if I calculated what's called Q, the reaction quotient, it would indicate that the Q is going to give us a forward direction. Let's suppose, with the stoichiometry involved, that the amount of nitrogen as it's consumed will be called X. Because oxygen is the same 1-to-1 stoichiometric ratio, it would also get consumed in the same amount minus X. Because products get made to the tune of 2x, we're going to call that value as first change, the value of 2x, a 1-to-1-to-2 stoichiometric ratio, pulling those coefficients down. So at equilibrium, we have 0.2 minus x representing the amount of nitrogen, 0.2 minus x representing the amount of oxygen, and value of 2x as the value of our product, nitrous oxide. The Kc expression will say the concentration with respect to nitrogen monoxide squared from the coefficient set over the concentration of nitrogen to the first power times the oxygen to the first power. Square the top and we'll multiply the bottom. So using this setup, Kc is given to us as 0.10. The concentration of the product is 2x squared set over the concentration at equilibrium, 0.2 minus x, times the concentration of the oxygen at equilibrium, 0.2 minus x. Let's solve for x, the value of the change in the reactants. First, I'm going to FOIL. Down below, 0.2 times 0.2 is 0.4. 0.2 minus x, 0.2 minus x. So I wrote that wrong. 0.2, make that bigger for us. 0.2 times x, 0.2 times minus x is minus 2x. And again, minus here with the 0.2, that's the inner part, minus 0.2x. And then here, negative x times negative x would be positive x squared. We can simply add together the like terms. 0.4 minus 0.4x plus x squared. That's just foiling, and you probably are very comfortable foiling. I'm just going to share those steps. Multiply the first terms, multiply the outer, inner, and last, combine the like inner terms, and we come up with our FOILed equation. I also have to distribute a 0.1 through that. Again, bringing that down, this is cross multiplying, distributing a 0.1. 0.1 times 0.4 is 0.04. 0.1 times 0.4 is 0.1 times 0.4 again. 0.04, but that value has x, plus 0.1 x squared. That's equal to, and again, all I've done is distributed that 0.1 through my FOILed factor. I'll simplify the top. 2 squared is 4, x squared. So 2x raised to the second power is 4x squared. We want to end up having an algebraic equation for the quadratic formula. So we want to set it to 0. So let's subtract 4x squared from both sides. I can combine these two like terms. So a negative 4 plus a positive 0.1 is negative 3.9x squared minus 0.04x plus 0.04. We now have come up with the term for the A, the B, and the C for our quadratic formula. Again, I just used the program for the quadratic formula. Under Programs, it's my quad, and it's going to ask me to type in the value of A, B, and C. Negative 3.9 is the value for A. Negative 0.04 is the value for B. And the value for C is positive 0.04. And we get two choices, 0.0962 and negative 0.1065. One of those choices is tossed out. There is no such thing as negative concentration. So x becomes 0.096, and I'll just round 3 molar units. So now that I know x, I can bring that up to my equilibrium chart and actually solve for the equilibrium concentrations. 0.2 minus the value we solve for x. So I can take 0.2 minus 0.096, and what did I round one more? 3. And those concentrations come out to be 0.1037, which is the concentration not only for the nitrogen, but it's also equal to the oxygen, since indeed they were given the same amount. I'm going to squeeze my unit there. Those are big M, molarity units. Alrighty. 2 times the value of x, the concentration of NO at equilibrium, .1926 molar units. Alrighty, setting up an ice chart, letting x stand for the value of how much reactant was consumed. The 1-to-1 stoichiometric ratio said both were equal to negative x. The 2, the twice the amount of product is made, let the product determined to be 2x. And then from there it's algebra, pulling out using the quadratic formula the value of x, going back to plug it into the equilibrium line to solve for the question asked, what are the equilibrium concentrations of reactants and products?